All right, how's it going, everybody? We are here on Thursday, January 28th. We're going to talk about section 6.3 today. Section 6.3 is going to involve a new method of integration for us to discover some volume computations here. This is going to be sort of an alternative to our techniques that we saw in section 6.2. We're going to see some scenarios today in which using our disk or washer method is going to be not that great for us, and we want to consider a different sort of geometric idea that we can use to accumulate area to achieve a volume. This section goes really nice with section 6.1 and 6.2. These should really be kind of teaching you in a very general sense how to think about how does integration really conceptually work in a geometric sense. Which is going to be really practical for us throughout the course of this semester here. So what we've seen so far is the kind of our three sections here are really just three different ways for us to think about what does it really mean to accumulate Riemann objects, right? In section 6.1, we saw the area between curves. So we said, if we can find a formula for the height between two curves or the width between two curves, then we can accumulate these vertical or horizontal lines, right? They were just one-dimensional lines. A Riemann stick is really just one-dimensional. And if we accumulated all of those Riemann sticks either horizontally or vertically, then we would arrive at an area. One-dimensional objects accrued to become two-dimensional objects. In section 6.2, we said, well, if a solid object is well described as a rotation of a 2D object about an axis. Now realize we're not talking about general volumes. You will talk much more about volumes when you get to Calculus 3. We've really only been talking about like rotationally defined volumes here, right? Sort of just a subset of all possible 3D shapes. But we said if the solid object is well described as a rotation of a 2D object about an axis, then we can accumulate disks or washers, right? And I think pretty often we end up with vertical stacks of these, but certainly it's the case that if we're rotating around a horizontal axis, we might want to be doing accumulating a horizontal stack of vertical disks or washers right there. Then we can accumulate those two-dimensional disks or washers as cross sections to arrive at a volume, right? So accumulating a lot of area pieces, two-dimensional pieces, gets us to a third-dimensional piece of volume. Today in section 6.3, we're going to say sometimes the disk and washer method goes poorly due to algebraic restrictions. One of the things that we have to be able to do with the disk washer method is to be able to define our inner and outer radii if we're looking at like a washer, and sometimes that gets to be difficult to do. Instead, it might be better to accumulate cylindrical shells, an infinite number of infinitely thin cylinders to arrive at a volume. So instead of thinking as accumulating volume from left to right, instead of thinking as accumulating area as sticks from left to right, instead of thinking of accumulating volume as disks or cylinders vertically stacked, we're now going to instead think about accumulating our volume as cylinders, one of every radius, to fill out a volume of an object here. In all cases, we need to compute the length or the area of the Riemann object, then add up the infinite number of Riemann objects. That's called integration. We'll follow the exact same principle here today. And the important thing is, since we're adding up an infinite number of hollow cylinders or cylindrical shells, that's just really just two sets of words for the same thing there, we need to be able to compute the volume of a single one so that we can find a representative, a general Riemann object with which to define kind of our terms for our integrand, the stuff that we're integrating here, right? So let's talk geometry first and then incorporate the geometry into our integrals here. So what we want to think about here is the general volume of a cylinder and the general definition for sort of the area or the volume of a shell of a cylinder. I guess this is our kind of more important one that we're looking at right here, right? So what I'm seeing here with this cylindrical shell, and this is hopefully a thing that you've kind of like, I don't know, like seen at some point in geometry here, is that like if we were to talk about the surface area of this entire cylinder right here, that really we think about cutting along this dashed line right here and opening it up. The circleness makes it a slightly more difficult area for us to discuss here, but we should see that if we cut this cylinder, if this is like a soup can, right, and if we cut off the top and cut off the bottom and then cut vertically a slice right here, that we could expand this thing to just be a rectangle with sort of like a circle there and a circle there. Hopefully you can imagine that this 2D shape right here, we could roll together the rectangle and then flop down those two circles and we'd have a can, right? So that's our kind of our creation of our of our the surface of one cylinder right there. And I think that this is like not an unusual. I think that you guys have in like Calc 1 have done things like what's the optimal dimensions of a can to make it cost the least amount of money. I think those are like optimization problems we all often see in Calc 1. We are slightly more interested in the shell here, but because this is going to be our Riemann object. This is the Riemann object that we're interested in, not a solid cylinder here, but a shell. We want to accumulate shells of all different radii. And so what we should see that's slightly different here is that the shell doesn't have a top or bottom, right? So these circles aren't there. And very importantly, a shell does have thickness. However, since we're thinking about accumulating an infinite number of these Riemann shells, they can't have finite thickness. The thickness is going to be the infinitely thin part right there, right? So when you see that there is this like white gap right here, that's the thickness of the shell, that's going to become our like dr term, our infinitely thin radius difference right there between the outer radius of the shell and the inner radius of the shell. Some other things that we can see are important are the height of the shell, which we'll be able to get from the output from a function describing our two-dimensional shape. And you can see that the other very important part about this is that we clearly need to know our circumference around this thing. We need to know what the distance is around, because ultimately our shell's volume, the volume of one shell, is the same as the volume of this rectangular prism right here. Is that my 3D word for that? This box that's right here. And what we can see is this has 3 dimensions right here. We can see that this has height h. We can see that this has a width of the circumference. And we can see that this thickness right here is sort of like the difference in radius. And so I know this is really, really small right here. This writing that's down here says, and I'll just write it bigger right here, delta r equals r2 minus r, wait, what is it trying to say right here? Oh, I see what they're saying right here. Is r2 minus r1. And we're really saying our average radius is, the sum of the 2 radii over 2 right there. But the point is, this is really like our delta r right there, which is what is going to come to be in our Riemann object, a dr. Right? Now we're going to end up seeing that our radius is going to be able to be measured in terms of x or y. So it's not like we're going to have r terms in our integrand, but we're still thinking about the radius, the distance from our axis of rotation, as being a key measure here for the volume of one object. So it looks like our total volume of this guy right here is going to be our height times circumference times radius. Right? Circumference times height times radius. Well, those 3 things are giving us the volume of this block, and the volume of this block is the same as the volume of the shell. It's just been unwrapped is the only difference right there. So I can see how we're going to compute the volume of one single shell. We want to accumulate an infinite number of these with an infinitely thin radius, so that this is really like a 2-dimensional sheet that we've rolled up into a shell, and we're accumulating an infinite number of sort of like a 2-dimensional shells to accumulate to a 3-dimensional volume here. So the volume of one shell is circumference times height times thickness, or radius, which we will interpret as circumference is 2 pi r. The height is just h. We're going to end up getting this from our function value describing the 2D curve that's being rotated. And this delta r is what's going to become dr when we allow the limit as n goes to infinity of our number of subdivisions, our number of shells tends to infinity. They become infinitely thin. That delta r will be our dr right there. R is our distance from the axis of rotation. So I think the only other thing that's kind of good to visualize in this picture right here is that there should be a line that's going down through the center here, where we are rotating about this axis that is centered right there through the shell, right? So we're rotating about the center of it. That's going to be our radius r, is our distance from the axis of rotation. In the above diagrams, since that shell is a vertically oriented shell, we can see that our radius here would be equivalent to like a measurement of x, right? It's a horizontal thing. However, hopefully you can imagine it might be the case that we want to have some laying down shells that we accumulate that grow out from a horizontal axis of rotation. So it might be the case that y's are involved with our radius. It just depends on our setup of the problem that we're looking at there. H is the height measured parallel to the axis of rotation here. So our axis of rotation is vertical. Our height is also measured vertical. So those are parallel to each other. The thickness will be limited to being infinitely thin. It's going to be not just delta R, but dr, which in this particular case, because the shell that's graphed vertically over right there, or because the shell is graphed right there is vertical, the radius is a x measurement, a width measurement. And so in this case, dr would be the same as dx in that picture, but again, that can change here. Therefore, what we're going to end up measuring here is that our volume is just going to be exactly, or we want to accumulate all of these volume pieces, but one for each of our infinitely thin shells. And so we will sum up, add up, integrate circumference 2 pi r, which in our above picture is x, times the height, which we get height of our functions as f of x, times the infinitely thin radius. And again, in our above picture, our radius actually was x, but again, that might change depending on our setup. And again, evaluating this as typically what we do with our integrals here, from an a to a b, from the innermost to outermost radius values that's out there. So what we want to ask ourselves here, and that's what I'm getting at with this bottom line down here, is why are we doing this if we've already talked about accumulating volumes with discs and washers? Why are we just getting a second technique to do something that we're already capable of doing? So really just the examples that we want to do today, just kind of want to like highlight that in many situations our cylindrical shells are a much better strategic choice for us to make to accumulate volume. And so we want to be aware of both methods so that we can choose for ourselves what we think the smartest way is to express any volume. So let's look at our first example here. Let's find the volume of a solid obtained by rotating about the y-axis, the region bounded by some cubic, and the line y equals 0 here. So I guess first things first, we need to understand what our 2D shape looks like so that we can see what it'll be like to accumulate our discs or washers. So let's real briefly pop over to Desmos and let's have Desmos graph this now. By the way, I just want to say real quick, 100% you need to be able to graph things like this by hand. Don't use Desmos as a crutch in your life. You can graph cubics. If you can't graph this cubic, that's actually kind of a problem. You should be able to do this without Desmos. I'm still going to get a Desmos picture because I want nice graphs, but I'm seeing here for myself at least that I should be able to write 2x squared minus x cubed. I can factor out an x squared. And so I know that this is a cubic. I know that it has one root at 0, and I know that it has one root at 2, but I know the difference here is that the root at 0 is a double root. It's got even multiplicity. And so I know that this is and last thing I know is that this is a negative cubic. So I know that this should have a downward trend, right? I know that my end behavior looks like this because it's a negative cubic. I know that we will have a point of tangency at the origin because our x equals 0 root occurred twice. And we'll also pass through x equals 2, but it's a single root. So our graph should be something like that guy right there. And again, you know that, and you should be able to do that. There's nothing wrong with computer-generated images, but don't forget that, yes, you're still expected to know algebra here. So let's go to Desmos and get a clean picture because I don't want to try and draw Riemann sticks on that thing right there. So let's pop over to Desmos here. And in Desmos, I can go ahead and graph this. This was 2x minus x cubed. Or sorry, 2x squared minus x cubed. There's exactly the picture that I drew there, just obviously a cleaner version of it. I'm going to zoom in since I know that I am interested in, and my description, by the way, back over here said, we are interested in rotating this about the y-axis, the region that's bounded by this curve, and y equals 0. So it seems to me like we're just interested in just our little piece that's right there in the first quadrant. That's what's bounded by both the curve and y equals 0. So I kind of just want to see this first quadrant stuff, and we're going to revolve it around the y-axis right there. So back over to Desmos. I kind of have this kind of sitting right where I want it here. I'm just going to go ahead and get rid of, I don't need those minor grid lines right there. And honestly, I don't know, do I even need the grid at all right there? I think I'm good with just like a blank picture right there a little bit more. Let me snip this guy. Let's bring this back over to Microsoft Word. Why did I flip it? That was weird. Okay. Let's make that through. And I'm going to want another one down here for when we do our cylindrical shells instead. So what I'm saying here is let's do this both ways that we know how to accumulate volume. We did the disc washer method last section. Let's see what that looks like here. We're talking about cylindrical shells today. We'll do that second so that we can kind of compare these two strategies right here. So when I am looking at my disc washer method, the very important thing that I know is that we are rotating about this axis right here, the y-axis, right? So what that says to me is I can picture for myself that this is our area that we would like to revolve around the y-axis right there. So I'm picturing for myself that we could build a horizontal Riemann stick like this. This horizontal Riemann stick is the stick that's getting revolved around the y-axis to produce a washer. Right? So if I'm going to talk about the area of this washer, then I can see some things like, it looks to me like the radius is being measured as an x component here. It looks like the distance from our axis of rotation to the inner radius, I can just call that's just an x value, right? I don't have to do anything special. It's not like it's 2 minus x or anything like that. We're measuring from this axis of rotation to this edge. It's just some x value. I'm going to call it x sub little r because it's our little radius and it's an x component. Similarly out here, also just being measured as some x value for each of our washers right there. I'll call that x sub capital R for that Riemann stick right there. Right? So what I'm picturing for myself is this. I know that I am going to do a vertical stack of washers. It looks like our y values here are going to go from 0 up to something right there. I'm just going to put a question mark for right now. Y equals 0 to y equals, it looks like there's some upper bound. We got to go find some maximum y value that's right there. But I just want to get my general word integral out right here. So it looks like this should be the integral from 0 to question mark. I know that this is going to be a dy integral. And I know that my expression for our washer area is going to be our pi times our big R squared, which for us is x sub r squared, minus pi times our little radius squared right there. So we know that these radii are actually x values. I'm still tracking them with capital R and the lowercase r, but I know that these are x values. So it seems like what we need to do is we need to rewrite y equals 2x squared minus x cubed as an equation for x. And so my question to you is, can you solve that equation for x? That's not a question mark, that's an exclamation mark right there. So notice what our dilemma is here. We know that if we were going to use the disc or washer method, we would be creating a stack of washers, is what I'm visualizing right here. Because we're rotating around the y-axis, I wanted my washers to be perpendicular to the y-axis right there, horizontal washers that we're creating a stack of, a vertical stack of them. That means that I know that I'm doing a dy integral because there should be one washer for every y value from 0 up to whatever that maximum height was there, the local max on that cubic. Since that's the case, I wanted my pi times my radius squared. My radius is an x value, so that means I need an equation that's x equals so that I can get a y expression to replace x of r and x of r, right? Lowercase r and capital R. That requires me to be able to solve a general cubic in this case. And I can't do that. And technically I can. I could go look some things up to do that. But what I'm pretty sure I remember about general solutions for cubics is that they involve things like square roots of square root terms and stuff like that. And like to suggest that we're going to be able to integrate that seems kind of unlikely. Okay, well, they're going to get squared along the way. But the bottom line here is this seems like an algebra nightmare. And the other thing that I'm recognizing here is it seems like we got to go and do some calculus, right? I'm going to have to take a derivative, set it equal to 0, find an x value where we reach a local maximum, plug that x value into the cubic, just so that I can find my upper bound y. The things I'm seeing here is like maybe I could do this and it's going to take a whole bunch of work. The bottom line here is this doesn't seem like this is shaping up really nicely. It seems like there's some algebraic restrictions here. The fact that we need to be able to solve a y equals equation to make it an x equals equation is really algebraically restrictive. There's tons of scenarios in which we straight up can't do that, and this looks like one of them right here. So it looks to me like I kind of feel like I can build my word equation for this thing that's appropriately representative of the volume we're interested in here, but I can't actually get this into an integrable integrand. I don't know how I would actually make this be something I could work with right here is kind of the bottom line. So just before so basically what I'm saying is it doesn't look like this is going to pan out for us right here. I do want to just kind of draw one last little picture here to make sure that we representatively see what's going on here. And so in general, right, we're in our washer method right here. We've got, this is our length, x sub little r. This is our length, x sub capital R. And here we're saying our height is an infinitely thin washer. And remember, washers and discs kind of go hand in hand. This one's a washer just because it has a hole in the middle. All of our concepts surrounding those are kind of the same thing right there. All right, so this seems like very algebraically restricted. I can't solve for x, so I'm kind of screwed. And even if I could solve for x, recognize another thing that would have to happen is we would then have to be solving for x, getting like that plus or minus from a square root right there, because it seems like defining this thing in terms of x, you know, if you turn your head sideways right here, this isn't a function anymore, right? So solving this thing for x means we're going to get that same positive square root, negative square root, things like we've already seen last week. This just seems algebraically very, very difficult to try and apply the disk or washer method to this scenario right here. So let's go ahead and see what's going to happen if we attempt to look at our cylindrical shells instead. Instead, if we're looking at this as accumulating this volume by rotating this region in the first quadrant around the y-axis, it seems a little bit more natural to me to think of our Riemann sticks here as being one vertical component of a shell, right? So now I'm picturing, let's rotate this vertical Riemann stick around that y-axis right there, and what it's going to produce is one cylindrical shell. So this is my vertical Riemann stick, which when rotated produces for me my Riemann cylindrical shell. So rotating the vertical Riemann stick about y equals 0 produces a Riemann cylindrical shell. And I'm getting ridiculous with my it's a Riemann this, it's a Riemann that. But I'm always trying to express to you, when we talk about Riemann objects, they always are actually one dimension smaller than what it looks like. That rectangle looks two-dimensional, but we know that it has an infinitely small thickness, so it's actually a one-dimensional rectangle. When we revolve it around, it seems like we're coming up with a three-dimensional shell, but what we really know is it's actually a two-dimensional shell because it has an infinitely thin thickness, right? So this produces a Riemann cylindrical shell. Here we're thinking our thickness, r minus r, is infinitely thin. Right? There's in a sense this outer radius and inner radius, but as we allow our number of subdivisions, our number of shells to tend to infinity, the shells themselves must become infinitely thin along the way out there. Right? So what we're thinking to ourselves is the volume of one shell that's going to be our circumference times our height times our thickness. So what that says to me is the total volume is what I should get from adding up, summing up, integrating a whole bunch of these single shells right here that have an infinitely thin thickness right here. So I'm going to integrate the circumference times the height times the thickness. So let's talk about what each of the three of these components are here. First things first, we need to be able to talk about the circumference of one cylinder. We know that circumference, should write the word out one time at least. This is 2 pi r. And what we can see here in this diagram is that our radius, right, is just a measurement of x. Because we're measuring from the line x equals 0 out to some x value, the overall radius associated with every one of our cylindrical shells is exactly the x value associated with the shell's Riemann stick. And so in this case, we're going to get 2 pi x for our circumference. And again, circumference is 2 pi r. It's always going to be your job to make a judgment as to how do we define r in terms of x and y in the problem that we've got. In this one, it looks like our radius is just the x value of our Riemann stick right there. Next up, we need to know the height of this Riemann stick, the height of this cylindrical shell. And that one's really easy. The height is just its y value right here. And I know how to write my y value. This is like our f of x right there. It is the height of the curve. That's the height of the cylindrical shell. I've got a y equals f of x equation. It's in terms of x. This is really good for us. The last thing that we've got here is the thickness of this shell. And it looks like the thickness of this shell is a change in x value right there. It looks like the thickness is our dx right there. Again, it might be the case in other problems that you guys are going to do where there might be our axis of rotation is the x-axis, in which case your thickness would be a y value instead of your thickness being an x value right there. So again, it's up to you to be judging what do we do, how do we interpret the r terms that are associated with this. Technically here, thickness is dr in general. In this particular problem, our radius is being measured as an x value from 0. And so we are just getting here a dx term. So this seems to me, ooh, by the way, we've got one last thing to say here. Now I know that I'm accumulating these cylindrical shells from the y-axis, and we're growing all the way out until our final cylindrical shell will be built out here at x equals 2. So it looks like these x values, the radii that we're using, go from 0 out to 2. Yeah, stacking the shells is like the Russian nesting dolls. Yes, the only difference is like chop all the dolls' heads and feet off, right? It's like this. These are like open topped. But other than that, yes, they're all sitting one within each other, like perfectly sliding into the next one right there. Yes, they're all like layered cylinders within one another right there. Sort of like just take a bunch of sheets of paper that are all very, very, very slightly shorter than one another and just keep on taping them together, and they should all stack down together right there. Right, so the final piece I'm seeing here is what is the span of x values that we're considering here to build all these, and it looks like it's going from 0 to 2. And by the way, recognize that we could have found 2 by doing algebra, which we did do up top right there. I can see it visually in my graph here as well. So let's go ahead and do this integration here. It should be relatively easy. It looks like I'm getting the integral from 0 to 2 of 2 pi x times my function, the thing that's giving me my height. This was 2x squared minus x cubed. And what do you know? We've got a pretty dang easy polynomial integral to do here. I'm going to go ahead and pull the 2 pi out front, and I'm going to multiply the x through my other polynomial expression here. This will give me 2 pi times the integral from 0 to 2 of 2x cubed minus x to the 4th, because I distributed this x through our second polynomial part there. And now we're ready to integrate and evaluate, and we are good to go. All right, so integrating x cubed introduces the 1/4 that we add 1 to the power, which pops down to 1/4, minus the 1/5 x to the 5th, all evaluated from x equals 0 to x equals 2. Come on, pen. What are you doing right there? Love seeing bounds of 0 when we're integrating polynomials because all that stuff just goes to 0. So 2 pi times. So this is going to be 1/2 times 2 to the 4th minus 1/5 2 to the 5th minus 0 here, right? Because I plugged in 0, I'm getting 0 for both those components. And so our final volume here should be 2 pi times. This is really just 2 cubed, this first part right there, so that's 8. Minus, that's 32 over 5. That's 2 pi times 40 over 5 minus 32 over 5. That's 8 over 5 times 2 pi, which is 16 pi fifths. Yeah, that's what I'm seeing here. All right, so just doing a little fraction math, getting down to our result at the end right here. There we go, fall off the screen a little bit. So the point here being, this was literally not algebraically doable for us if we attempted to do this as cylinder or as disks, because accumulating those vertical disks would have required us to do some algebra that we, even if we can do it, I mean, do you honestly really want to go learn everything you need about managing algebra of cubics? And the answer is no. On the other hand, if we thought about accumulating our components differently here, cylindrical shells as opposed to flat disks or washers, we found a much simpler expression for a single Riemann object, 2 pi x times y times dx, a much simpler expression. Yes, Riemann beer cans. There we go. So, and exactly, we got to bring our own personal satisfaction into this. Exactly. Now we're making this fun, right? We're accumulating beer cans, an infinite number of them, one within the next. Now notice, just because we're accumulating an infinite number of beer cans, there's still only a finite amount of volume that we're accumulating in the overall amount out there, right? But again, this again is a comparison between two techniques, and I hope it's obvious that in this scenario, cylindrical shells was better. This is not to say that cylindrical shells as a technique is better. This is a scenario by scenario thing. So one of the things that we want to be kind of broadly learning here in chapter 6 is this isn't just about applying a technique. This is about strategizing. This is you needing to say, looking at this and saying, okay, let me see what my setup would look like for each of these two scenarios. Which one of these two do I want to pursue? Hopefully you're going to see by attempting to set up both that one of them is doable and one of them is not, right? So I think it's important to don't just look at our cylindrical shell method here, but see it as one of several options and understand that your ability to strategize is one of the big things that we want to take away from this. Your ability to say, I know that this problem would be better as cylindrical shells versus I know that problem would be better, which many problems are, to do as disks or washers right here. So it's not that one is better than the other. It's a scenario by scenario thing here. So recognize that this is part of building a strategy, not just knowing a single technique here. I'm gonna get some t-shirts made. The Riemann Brew House. Infinite cans but finite beer. Sad. So let's look at another example here. This one we will be able to pull off using both techniques. Let's do both techniques. Let's both do our slicing, our disc washer method, as well as doing our cylindrical shells. We will be able to make both happen. And again, the point here is, again, this is a lot less about like, can you find the right answer, and a little bit more about like, are you confident in your ability to think geometrically in terms of calculus, to think in terms of Riemann objects, think in terms of integration here. So let's go ahead and look at our second example here. It looks like we're going to take an area that is bounded by the root function and the quadratic function. We're going to rotate that area around the y-axis, and we're going to accumulate the volume associated with that rotation. We'll do this both ways, once with cylindrical shells, once with our disc and washer method. Oh, I got these burps this morning. So I think in this case I can draw my own picture just as well here. I know that we are interested in the square root of x function. Oh my goodness, I can draw this fine. Holy cow. Let's try that again. There we go. There's a square root function. That will look pretty good. And we also want our x squared function here. I don't think I need to do any algebra to any of you to justify that I know that that point right there is located at 1, 1 right there. I think we're all good with that part right there. So this is our area, our region of interest, is this little chunk between the two curves. This is what we are going to rotate about the y-axis right there. Right? So what I'm picturing for myself is it seems like we can define a Riemann stick that when revolved produces a Riemann washer. I'm just going to say that here. Rotating the horizontal Riemann stick about the y-axis produces a Riemann washer. As with the previous problem, it appears that, and I will switch just so that I can see this a little bit cleaner, it appears that our inner radius and outer radius are once again simply just x measurements from the y-axis right there, right? We're not revolving around like y equals 2. These are just x amounts that we have traveled from x equals 0 to the inner radius. So I'm just calling it, it is just an x value that we've got right there. All right, so if we're going to go ahead and draw our Riemann washer that we are producing here, I'm again just going to say it has x sub little r as its inner radius and x sub capital R as its outer radius here. And so its total area is going to be our same pi x sub capital R squared minus pi times our inner radius, lowercase r squared right there. We want to add up that area for all of the, yes, we're doing it looks like we're doing a vertical stack of washers right here. So we want to add up one of those washers for every y value from 0 to 1. So therefore, our volume should be the integral from 0 to 1, our area, dy, right? Which in our case here is the integral from 0 to 1, pi times x sub r squared minus pi times x sub little r squared dy. So we need x sub r and x sub little r in terms of y. Last time, that was literally a roadblock for us in the problem. We couldn't move forward because we were not able to solve for the x values in terms of y. It looks like in this case we're in a little bit better shape right here. It does seem that we can actually go ahead and do this guy here. So I'm thinking to myself, our first one right here, x sub little r, which function is it associated with? Our x sub little r seems to be a measurement associated with the square root function right here. Right? And again, stop and look at the graph. X sub little r, our inner radius, is always being measured by the square root function, whereas our outer radius looks like it's always being measured by the quadratic function's width right there. Right? So I'm identifying that the inner radius is associated with the square root function. My intention is to solve for x here to know what x sub r really is. This is now my x sub r right there. And it looks like I can just square both sides. So x sub r should really just be y squared. So that's one of the expressions that I know. Very similarly, for x sub capital R, I can tell from my picture that x sub capital R is a width that's being measured by the quadratic function. So I'm going to say that this is our y equals x sub r squared, right? So y equals x squared. I'm now identifying that that x value is what I'm referring to as x sub capital R. My goal is to solve for x, and so I think that I can just go ahead and take a square root on both sides right here. I can see that since we're interested in hanging out in the first quadrant, I'm only interested in the positive thing that we're getting out of the square root here. Technically, there's a plus or minus. I'm only interested in the positive component that's in the first quadrant right there. So in this case, we are able to do the algebra to convert our y equals equations into x equals equations, and therefore it's still acceptable for us to be doing our disk washer method here. So I think now we can go ahead and compute our volume. So our volume should be, we're accumulating one washer for all the y values from 0 to 1, a stack of washers from y equals 0 to 1. Our area of one washer is pi times the outer radius squared, which it looks like is our square root of y squared, our outer radius squared, minus pi times our inner radius squared. and that's the thickness of every washer. Every washer was dy thick because they were being vertically stacked. So the height of a washer was infinitely thin vertically, and so it's the dy component right there. We look like we're in pretty good shape. The one thing that's kind of worrisome is that there's a square root, and we're squaring it. We're in polynomial land here. So I'm going to go ahead and factor out pi, because that's just a constant. And it looks like all we've got here is just y minus y to the fourth. That's a pretty dang easy one right here. All right, let's integrate this guy, see what we get. Then we'll do it the other way, confirm both our answers are the same, and we'll be all happy with the geometry we did here today. So I'm seeing here 1/2 y squared minus 1/5 y to the fifth. Evaluated from y equals 0 to y equals 1. Couldn't be anything better than evaluating a polynomial integral from 0 to 1. It does not get nicer than that. Plugging in 1 just causes us to keep our coefficients. Plugging in 0 causes everything to go to 0. This is just pi times 1/2 minus 1/5, which is pi times what? 5/10 minus 2/10. So we're going to get 3 pi tenths is the total volume right there. Okay. So again, this is section 6.2 stuff right here. We just did the disk washer method on this guy, and the reason that was a reasonable thing for us to do is because it was reasonable for us to be able to solve our equations that were y equals equations into x equals equations right there. Now let's go ahead and repeat this, but let's instead use cylindrical shells, and so that we can kind of have a comparison between the two methods. In this case, I think that we'll find that these two methods are kind of relatively comparable in this case right here. I would say that I'm not necessarily thinking that one of these is wildly better than the other in this case right here, because our equations were so easily algebraically manipulatable. What's my word there? Easily able to be manipulated. So when I'm picturing my shells here, again, the important thing is that since I'm rotating around the y-axis, that means that I know I want my shells growing radially out from that axis of rotation. So that's how I know for a fact that I'm going to be building vertical shells here, right? Just like in our previous one. So it seems again like my shell's height is going to be determined by our function values, but now notice my Riemann stick isn't sitting on an axis like it was in the previous problem, so we're going to have to be a little bit smarter about how we accumulate our parts here. So we need to identify, again, this is our y equals square root of x, this is our y equals x squared. I don't know why I started this so dang close to the last one right here. In fact, can I not? Is it going to let me? Yeah, grab all that stuff. Drag it. Now, drag it. No? See? That's close enough. I'll take that. All right. I just want to move this so these are separated. All right. So again, because our axis of rotation is the y-axis, I know that my shells are rotating around that y-axis, so I know that I'm vertically building my shells around the axis of rotation here. So we know that to do our cylindrical shell method, our volume is going to be an integral of circumference times height times thickness. And we want to identify all these. Don't be afraid to write word equations for yourself. Obviously, I can't do math here yet. This is me being well organized. This allows me to, instead of trying to do things like just blurt out an integral that we want, allows me to think about this piece by piece by piece. Yeah, remember with googly eyes, yes, the orientation of the rotational axis will always determine the orientation of the shell. It should always be the case that our axis of rotation is the dead center of every shell. When we say thickness, When we say thickness and when we talk circumference, both of those are dependent on a radius, and that radius is being measured from the axis of rotation. So because this is a y-axis rotation, it's got to be that we have vertical shells. If this was x-axis rotation, then it would be that we would be using y components for thickness for our radius and stuff like that, right? If we were rotating around the y-axis, then now our radius is measured as a y component. And when we when we rotate around the y-axis, our radius is measured as an x component right there. And that's the only thing that changes, just the labeling of the variables. And very, very honestly, in so many of these problems, you could just reorient every single thing geometrically to be like vertically around the y-axis if you wanted, just by changing some variable names and shifting some things around. You know, volume is the same no matter where it's located or how it's oriented in the two-dimensional or three-dimensional plane. So like, you can kind of build these however you want. Certainly you're going to be suggested some equations and some axes of rotation, but like volume is volume no matter where it is or what way it's pointing. And so technically all these variable choices that we're making are a bit arbitrary here. So what do we got to know? We got to know the circumference here, and then we know that our circumference is always our 2 pi r, so maybe I'll just write that for right now. The height of this Riemann stick. What's the height of my Riemann stick? Well, I can see here that this goes, we've got kind of like a top height, y2, and a bottom height down here, y1. I guess what I can see is the height of my general Riemann stick, the stick that's used to produce the Riemann cylindrical shell, has upper height of root x, but we don't care about the height between the axis and square root of x, right? So we want to subtract that guy off. So it seems to me like my height in this case should just be our y2 minus y1. We'll identify what functions those are in a second, but I can see it's like my upper height minus my lower height gives me the actual height of that one cylindrical shell. And finally, what's our thickness here in this case? How thick is that shell? Well, I can see that the thickness of one shell right there, that's our delta x or our dx right there. So for my thickness, how thick was that thing? It was dx thick. That's our infinitely thin component. So it seems like if we want to finish this guy off, what we still got to do is identify bounds of integration. We need to know what r is in our circumference expression, and we need to know what y1 and y2 are in our height expression. But otherwise, we're moving along here, kind of making some progress, right? So some things that I'm seeing are this. One, since this is a dx integral, I know that I'm interested in identifying bounds of integration that are describing all the x values of interest for us. I can clearly see here that my x values of interest, my Riemann sticks, are going to exist from x equals 0 out to x equals 1. So one piece of information I can fill in is I'm pretty sure we're doing 0 to 1. And honestly, this is one of those ones where it's like, also the y stuff goes from 0 to 1 right here. I'm hoping that you could just straight up guess 0 to 1 even if you didn't know what you were doing, right? Even if you thought about this wrong, the y's are also going from 0 to 1 here. It's nice to have symmetry, isn't it? Next thing here, we're going to decide what's the radius of this shell. Well, our radius right here, from our axis of rotation out to our general Riemann stick defining our shell, well, that is just our x component right there, right? Just like delta x was going to dx, which was our infinitely thin change in radius. It looks like our radius in this case is just x because we're measuring from x equals 0 out to a general x value. So the total change was x. That's our radius here. So I'm getting a 2 pi x. What's y2 and y1? Well, we've measured y2 to be the height associated with the y equals square root of x function right here. I know that I want x stuff in this integrand because this is a dx integral. So when we say y2 right here, this is measuring the height according to the square root of x function. So when we say y is the same thing as square root of x when we're talking y2. Minus, when we talk about y1, that's our lower part, and that's always associated with our quadratic function. So in this case, our y component is measured as x squared. Boom. We're pretty much done here right now. Now we're doing the boring part, actually integrating. I already made a mistake. I don't need that 2 pi there. You're always going to end up with constants that might as well be pulled out front of your integral here. Very similarly, like the last one, I'm going to distribute this x through. Last algebraic thing I'll say, having radicals is rarely useful to me when I'm doing derivatives and integrals. I always want these expressed as powers. I'm thinking of this as x to the 1/2. And so when I multiply by an additional x, this will be x to the 3/2 total right there. So integral from 0 to 1, x to the 3/2 minus x cubed dx, right? I pulled 2 pi out front. I distributed the x, rewriting this as a fractional power instead of a radical. And we're as far as I'm concerned, we're essentially done here. Add 1 to the power. That becomes an x to the 5/2. That means I should introduce a 2/5 as my coefficient there, so that when I take the derivative, 2/5 and 5/2 become the coefficient of 1 that we see sitting right there. Minus, this should just be a simple 1/4 x to the 4th. We're evaluating this guy from x equals 0 to x equals 1. And what do we end up with? I'm hoping our previous answer that we've already done. 2 pi. And again, nicest thing ever is a value. Technically, this isn't a polynomial. 5/2 power is the whole number power, but we still get the same features. That is, 1 just leaves us with coefficients. 0 makes everything go to 0. So we are, again, getting 2/5 minus 1/4. And that is going to give me 2 pi times, we want to get 20ths here, so that's 8 20ths minus 5 20ths. And that's going to give me 2 pi times 3 20ths. 2 cancels with 20 to give me 3 pi tenths, just like we got a second ago right there. Right? So that's the only examples I wanted to do for today. And notice that all we did today was just talked about geometry. I don't really feel like we introduced any new calculus ideas today. The only thing that we said is if you need to add up area to get to volume, there's lots of ways to express area. Instead of expressing the area of an infinitely thin washer, we can talk about the area of an infinitely thin cylindrical shell. As long as you know that the volume of a cylinder is the circumference times the height times the thickness, that's all you need to know to extend your already existing integration knowledge to be able to use this technique right here. So I think that a thing that is like our big takeaway from the day here is that when we're doing cylindrical shells, there's nothing really fancy about this. Now that we have this general concept that integration just says add up an infinite number of n-dimensional Riemann objects to get an n+1 dimensional object, here we made 2-dimensional sheets. We rolled those sheets into cylinders. We accumulated an infinite number of those cylinders, and we got a volume right here. Are you asking down here, chemistry bros? That x going to 1? As far as my evaluation goes here. So again, recognize this for just some geometry. And I think that that's going to be kind of, in a sense, really, really nice for us right here. I, again, want to heavily stress to you guys, labeling lots of things, using words in integrals, even though integrals are supposed to be for math expressions, it's a really, really, really beneficial thing for us to see right there. So do write stuff like this. I know that you're not going to do math from this line. This is our organizational step right here. It's okay to have r's and y's in a dx integral as long as you understand that you need to get everything to be in that single variable right there to do the integration, right? And so as you're talking about there, chemistry bros, this guy down here in the bottom, just the nicest thing ever about having polynomial stuff come out of an integral is that when we plug in x equals 1, so you're talking about this second to last line here. When we have x equals 1, plug in 1 to the 5/2 is 1, so we just get 2/5. 1 to the 4th is 1, times 1/4 is just 1/4. So that's why the only part I kept when I evaluated here was this. When I plugged in 0, 0 to a power is 0, so that goes to 0. 0 to a power is 0, that goes to 0. Plugging in 0 left me with nothing. Plugging in 1 into our antiderivative only left me with those two coefficients. So 0 and 1 are very typically like the nicest possible bounds of integration you're ever going to get, especially with polynomial and root functions, just because it just washes some stuff away. So you're talking about just doing our fraction math right here. Yeah, I got my common denominator with the basis of 20. 8 minus 5 gave me 3. I canceled a 2 with the 20 to make that actually a 10 in the denominator. And that's what left me with 3 over 10 times pi, or 3 pi tenths right there. Yeah, just a little bit of evaluating right there. So yeah, 0 and 1, best bounds ever when it's polynomial stuff. In a couple sections, we're going to get some trig stuff, and you're going to get all excited when we get bounds from 0 to pi. Obviously, the stuff that makes trig stuff pretty nice right here. So that's all I kind of wanted to do today was just a couple of these examples. I don't think that you need to see a bunch of crazy cylindrical shell method stuff right here because it is a geometry problem. If you can identify the circumference, the height, and the thickness in terms of the one variable that you want, then you're good to go, just like you were good to go with your disks and your cylindrical shells out there. It's definitely going to be the case that in the homework you're going to see some cylindrical shells that are oriented along the x-axis. That's literally just you're going to do y stuff instead of x stuff in your integrands. You're going to see some that are rotated about the line like y equals 4. Your radius is going to be things like 4 minus, or sorry, y equals 4. Your radius will then be 4 minus y instead of just y, stuff like that. So I don't think those are too big of crazy steps up. I think that it's easy to handle those things when you write these first two lines like this to help yourself. Because if you just throw a radius in there, that allows you to stop and yourself think, from the axis of rotation, how far is it to the general cylindrical shell that I've drawn right there? And you can judge that, just that one little piece of it by yourself right there. Hey, no problem. So doing these helps you. This is our like divide and conquer technique right there. I hate the phrase divide and conquer technique. That's just saying if your goal is to just blurt out one correct integral, like our third line or our fourth line right here, it's ridiculous. Nobody really does that. Stop and think about what each of the three components are. Stop and think about what each of the terms must be in each of those components. Break this up into lots of small problems where you can answer them one by looking at a picture. Don't expect yourself to ever just write down this third or fourth line right here. Expect yourself to write at least one of these two first lines right here and then decide individually, term by term. Now, what should R be? What should height be? Am I doing dx or dy? Am I accumulating these things radially out in the x direction or radially out in the y direction? Stuff like that. And so recognize cylindrical shells for the geometry problem that it is, saying this isn't too bad as long as you can think geometrically right here. So those are the only two examples I really think I need to do here today for these guys. If you guys end up getting stuck in the homework, I'd be happy to throw up some more examples there in Canvas. If you guys have seen, I've got some homework help from week 1 and week 2 stuff. You guys ask me questions, I'll do some problems and throw stuff in Canvas. So if you want to see any more, let me know. But I think that this is going to be good enough to get you guys going for all your cylindrical shell things pretty well here. Next video that I'm going to do tomorrow is going to be on section 6.4, which is titled very simply Work. I don't like that title because people who aren't physics oriented don't recognize this section for what it is, but this is going to basically be our first physics application section. I really, really like these sections, even though I have like a little bit of fear in my heart that like Eric Kramer is going to be looking over my shoulder, judging me for me not being a physicist. I think I do pretty well with these sections though. Don't worry, Eric's approved of my physics teaching right here to at least the degree that he's seen it. So we're going to talk about some things like work. We're going to talk about spring forces, pushing on walls, picking things up. How do we measure the amount of work that is done in a physical setting here? And so this is my kind of last comment going into 6.4. Just remember, even if you're not a physics person, remember that calculus was literally invented specifically to do physics. So even if you're not a physicist, this is like where everything comes from. The reason that we developed all these techniques was to do physics problems. So for at least for the historical purposes of this class, this is directly relevant here. And I think you'll see that we'll do some pretty cool problems with our work things in tomorrow's video. So I'll see you guys for our first section of physics applications. We will get a little bit more physics application stuff out in section 8 or in chapter 8. So we'll see a little bit more of it later as well. Thanks for being here today, guys, and I will see you for our next video on 6.4 to wrap up week 3 stuff with section 6.4. I'll see you guys then.